Hello friends, and welcome to another tutorial on Geeks for Geeks. In this video, we are going to understand the program which finds the height of a binary tree using recursion. Let us begin and first understand what exactly height of a binary tree means. There are two conventions to define height of a binary tree. In the first convention, we find the number of nodes on longest path from root to the deepest node. And in the second convention, we find the number of edges on longest path from root to the deepest node. We will follow the first convention. Let us see an example and find the height of a binary tree. In this tree, we have root node equal to 1. So, the longest path we can go is from 1 to 4 or 5. So, the height is 1 plus 1 plus 1, which is equal to 3. The idea is to recursively call height of left and right subtrees of a node and assign height to the node as max of the height of two children plus 1. Now, let us see the algorithm which will assist us in finding the height of a binary tree. Let us also have a sample tree to test our algorithm. First, we pass the root node which is 1 into function max depth. So, node will point to 1. Since node is not null, we enter the else part. Now, we will calculate the depth or the height of the left and the right subtree and return the maximum of the two plus 1. We call the max depth function recursively to achieve this. We have LDepth variable to store the depth of the left subtree and RDepth variable to store the depth of the right subtree. First, we have LDepth with the left child of 1, which is 2, passed as parameter. Since 2 is not null, we move on to the else part. Now, LDepth will be equal to max depth 4, which is the left child of 2. Now, the left child of 4, which is null, is passed to the max depth function. Since node is null, 0 is returned. Now, we move on to the RDepth. The right child of 4, which is null, is passed into the call stack. Since node is null, so 0 is returned. Now we compare the larger of the two and return the larger plus 1. Since both are equal, we return 0 plus 1, which is equal to 1. So, LDepth of 2 is 1. Now, we move to the right depth of 2. We pass the right child of 2, which is 5. So, node will point to 5. Since node is not null, we enter the else part. Now, the left child of 5 is passed, which is null. Since node is null, we return 0. Now, we pass the right child of 5, which is also null, so we return 0 to RDepth for 5. Now we return the max of RDepth and LDepth plus 1. Since both are 0, we return 0 plus 1, which is equal to 1 to RDepth for node 2. Now we compare the LDepth and RDepth for node 2 and return the greater of them plus 1. Since both are equal, we return 1 plus 1, which is equal to 2. Next, we move on to the right subtree of node 1. The right child of 1, which is 3, will be passed. So, node will now point to 3. Since 3 is not null, we enter the else part. Now, the left child of 3 is null, So L depth will be equal to max depth of null. Since node is null, 0 is returned. So L depth for 3 will be equal to 0. Now the right child of 3, which is also null, is passed. So 0 is returned. Now the max of L depth and right depth plus 1 will be returned. So 0 plus 1, which is equal to 1, is returned. Now we find the max of L depth and R depth for node 1. Since L depth is greater than R depth, we return L depth plus 1, which is equal to 3. The final value returned is the height of the tree. Now let us have a look at the time complexity of the program. This code will run in big O of n complexity. Here n are the number of nodes in our tree. With this, we come to an end of this tutorial. For any doubts or suggestions, please leave them in the comment section below. Thank you for watching.